And that will be, yeah, I should get them graded this afternoon, tomorrow morning, so you'll have them back as a reference to use on the final if you so desire. So moving into fluid dynamics. So I realized that I kind of jumped ahead of myself yesterday. In the paper lab I assigned you, most of it was dealing with gas laws, but then that last question actually was dealing with fluid dynamics. So in my head I had already studied it, so I figured you would know it. I gave you that question, but I was planning to hold that question till today. But now you've done it, so learning about it should hopefully make more sense. We'll see. But in your book, page 5, starting, yeah, page 5, chapter 5, page 26, is where we are at for fluid dynamics. So moving on from gas laws that we talked about yesterday, and trying to get through page 33, fluid mechanics, Pascal's law, Bernoulli's principle, and sound. So if you discover something new, you should have an interesting name, because that sounds cool. But if you don't, it's okay. So when we talk about fluids, fluid is a form of material defined as whose molecules are able to flow past one another without destroying the material. So I can take my water and slosh it all around, no matter how I turn it around or turn it upside down. It's still water. I don't destroy it. I can still drink it, and it gives me sustenance. So by that definition, gases are fluid and liquids are fluid, but the difference is that gases are very compressible. So I have my little syringe up here filled with about 6 cc's of air, and if I close off the end, I can squish this down about 1.5 milliliters. So I took that volume of air and I can really squish it. But fluid, or yeah, they're both fluid. Liquids, which I have this one filled with water, are for aircraft maintenance considerations considered incompressible. So I have the same amount of water in this syringe as I did air in this one. And if I try to compress it, seal off the end, and I cannot. Anybody want me to aim it at them? I keep it in my pocket to keep you awake. So yeah, very easy to see when you try to squish water, you cannot. I'm going to trust you to not squirt your neighbors. Let me see. Okay, I do have right there 6 mLs of water. If there's any less, I will know.
What about the teacher, not your neighbors?
No. Oh. You can try to squish them. It gives you something to play with while I talk. So, where this comes into play is on a, I don't have a picture of it, but a radial engine where you have your cylinders coming off at angles in a circle. So what do you think might happen if your radial engine is sitting there and you have liquid or oil from all your cylinders overnight all drained down into your bottom cylinder, and that oil kind of builds up in there. You hop in and you fire it up.
Hydraulic lock.
Hydraulic lock.
That picture there.
This picture right here. Yes. So you get what's called hydraulic lock. You'll learn about that maybe Ryan's precept class. But it will bend metal because that liquid is so incompressible. It will become stronger than this, and this will bend, and it'll be a very bad day. So that's something you're going to learn about in recep class. There's things to do to prevent that. But our gases, thankfully, are compressible. Otherwise, when you go to had the incredible opportunity to go to Israel, oh my, several years back. And we went to the Dead Sea, and the Dead Sea is very dense because it has a lot of salt and minerals in it. And it was very easy to float because it was much more dense than just regular like pool water. So there was more buoyant force for the volume of myself. But if this example is in your book, you take a 10-pound block, drop it into this fluid. If you start it out with a fluid filled right to the edge of this overflow pipe, it will pour out the volume of fluid equal to the volume of this block. So that's just something to know. Anybody ever, okay, I have a younger sister, I love her to pieces, but if she would ask for ice in her water, when I give myself ice water, I put the ice in and then pour the water in, but for her, I would fill her cup almost to the brim with water and then put the ice in, and of course, just spill out over the top and she would try to drink it. Long time, of course. Oh, I forgot, I made that now. Okay. So where this comes into play in aviation is we have airships where we fill it up with helium or some type of gas, and it becomes lighter than air. So the air, or the atmosphere, is a buoyant force holding up whatever gases are in here. And float planes, worst case, he's not paying, he's probably actually studying. Float planes are designed so that the buoyant force of water holds them up. Now here is a little tidbit of information you'll learn about, I think we talked about it in sheet metal class, we talked about floats. But according to regulations, the float size has to be 80% larger than the actual minimum required to hold the plane up. So that's why you see so much of the float sticking out above water, because of 80% greater than what actually would work. Now I'll talk about fluid pressure. So this is, or pressure is the force exerted per unit area. So area is a very important thing to think about when talking about fluid pressure. Zach, if you trusted me, you had your hand out here. Would you rather me drop the brick like this or like this? And why? Sorry, there's more area. The weight is distributed.
I hope we weren't going to test that.
I'm not that cruel. Only if somebody's sleeping. Not even that. I'd do this syringe of water for her. But yes, because we have a certain amount of weight, but when it's this way, I won't drop it. I'm not sure how sturdy the floor is. This distributed over much larger surface area than if I do it onto this edge here. Something with fluid pressure, fluid pressure changes with height and not with shape. So what that looks like, this is in your book. We have 3 columns of water here, or fluid, whatever it is. And each of these are 231 inches high. You can throw out whatever number. They all have the exact same height. And each one is exerting the same pressure per square inch. Doesn't matter how big or round they are, or if they're square or a circle. It is the same pressure at the bottom per square inch from one to the other. We're going to use that bit of information in just a minute. There are 2 types of pressures you'll need to be familiar as head pressure. So if I have fuel tanks up here in my wings, in my high wing Cessna, let's say, and way down here at the itty bitty bottom is my carburetor. If that carburetor needs 2 psi to function of fuel, then that tells the manufacturers how high they need to place the fuel tanks if there's no fuel pump. This is just based on gravity fed system. How high to get that 2 psi because height determines pressure. So that's how that will go into aircraft design. And that's very much like some of our stubbies and things we've created, why sometimes we have trouble with fuel flow because we might not have that tank high enough to get the right pressure at the carburetor. Then there's something called ram pressure, which is fluid in motion, or velocity converted to pressure. So we talked about ram air cooling. When your aircraft is taking off and then you're flying, you have pressure coming in the front of the cowling, right like this, coming in, and the air pressure is going over your cylinders, helping to cool it. When we get into turbine class, I do not have a picture of a turbine engine, but there is static pressure measurements, and there will be ram air pressure measurements, and all that is taken into account to do fuel adjustments and all kinds of stuff. So just right now knowing there's a difference between static pressure and ram pressure. Any questions on that? Now we get into some more laws. This one comes from Mr. Pascal. Way back in the day. Oh, just walked out. Oh, man, he missed it. He missed his moment. Missed his moment. So what this, I don't even know his whole name or when he lived. But anyway, he discovered that pressure force is transmitted through a fluid and it acts equally in all directions. So what that's saying, if I here have a piston, or yeah, piston, and I push on it with 5 pounds of force, then we come here, pressure that's felt through the system is equal to the force, which is 5 pounds, divided by area. So that's where the area comes in. So if I had a smaller piston or a larger piston, that's going to change what that pressure actually is from the force. So my force of 5 pounds pushing on my piston, which is 1/2 inch. So that's 5 divided by 1/2, which gives me 10 psi. That 10 pounds of pressure per square inch is the same on this side here, over on this side here, down on this side, the same throughout, because pressure is transmitted equally in all directions in a fluid. Whew. I thought I was done coughing up my lung this morning. So here is what I was showing you yesterday in that last problem on your paper lab. We worked through the formulas, but I didn't give you this fancy little triangle. So force, how much force we're pushing or applying, equals the pressure times the area. Or, because good old algebra always works, pressure will equal the force divided by the area, or area will equal our force divided by pressure. For my final, for lab, page 5-29, grab those formulas and use them. In the oral, you're not allowed any resources as of yet. That may change. So this is something you might want to memorize, or the written also. You're not allowed, but I have seen so far on your writtens, you're given one of these formulas. You might have to switch it around, do a little bit of algebra, but you'll be given one of those. But if you do like to memorize things, you can memorize force over area times pressure. And the way this works, so force here equals pressure times area. So if they're next to each other, that means multiply them together. Or pressure equals force if it's underneath, like here. I mean, this divided. So just like you would set it up. And then area equals force divided by pressure. Any questions on how this little diagram works? So here's what we had worked through yesterday using force, area, and pressure. And practically speaking, when you're going to use that as a brake system, so we can take a small force over a long distance up here at your brake pedal and transmit it to a very large force over a short distance down here where your brakes are working. I think Case will be teaching hydraulics class. I'll get way more into that, but just so you know, you can use this to your advantage long distance for bigger force, or you can do it backwards if you need it in any certain application. Questions on force, area, and pressure when dealing with fluids and liquids? We're going to move into another fine fellow, Mr. Bernoulli. So Bernoulli liked to play with toys, and he came up with this funny looking thing that's squished in the middle, and it is called a venturi. It has this wide portion here, narrows in the middle, and then widens out again. Again, in turbine, we're going to talk about a whole lot of how this helps pressure changes in a turbine engine. But what happens, what you need to know now, is as this narrows down, the velocity of our fluid through there increases. So it's going happy on its way, all of a sudden it gets narrow, it goes shoo! And the pressure decreases. Then when it widens out again, our velocity slows down, but our pressure increases. So here we have a duct that is converging. So that's called a convergent duct. And then as it widens out, it's called a divergent duct. Again, just start to get familiar with these terms. In turbine class, we're going to talk way more about them. But remember, as it converges, it speeds up, velocity increases, pressure decreases, and then as it opens up, slows down, but increases pressure. Where you're going to see this is in aircraft carburetors. We use a venturi to help get fuel into our carburetor. And tomorrow we're going to talk about aerodynamics and how venturi effect, the shape of the wing, kind of creates a venturi effect to help create lift. And then as I talked about turbine, jet engines, you can see here we have kind of a converging duct, a diverging duct, and a converging, and diverging, and that's all designed to create specific pressures or velocities. But I won't get into that now. I'll say that. I will be here for 3 weeks. Questions on Bernoulli's principle? Now, we'll talk about sound. So, by definition, sound is a series of disturbances in matter that the human ear can detect. That's what textbook is using for a definition. There's a whole argument if a tree falls in the forest and nobody's there, is there still sound? We won't get into that. But for sound to occur, you do need a source, so something creating the sound, something moving, vibrating, causing vibrations in the medium, which is going to carry the sound, and then something to detect it, like our eardrum, which senses those vibrations. So, or yes?
By that definition, the dog whistle obviously sound, even though the dog hears it.
Right, if you're defining it by the human ear, then technically, but something is detecting it. So if you go with a definition, it needs a source, medium, detector, the poor dog sure is detecting it. So, yeah. I would say that counts. So sound travels in waves, and we're not going to get too technically into detail on this, but it's waves with vibrating particles. So if you hit a tuning fork, I don't have a tuning fork, but I do have these wrenches, and see if this works. So whoops, I hit it. Oh no. So you hear that, and this is actually vibrating ever so slightly. That's how you can hear that being transmitted. And this one's heavier, so it's giving a deeper sound. But this, because it's making sound, you cannot tell, but actually is vibrating. And as it is vibrating, it is pushing little particles in what is called compression. The little particles get closer together, and then rarefaction just means they're spreading out. So they're compressing, spreading out, compressing, spreading out. So looking at it another way, it looks like a wave, which is how typically we think of sound as a sound wave. Or you can think about it as dropping something into a bowl of water, and you see these waves kind of moving out, one pushing it against the next one. So that I can stand up here and talk, and my voice is traveling in waves the whole way back to Samuel. So the speed of sound is determined by density of what the sound is traveling through and elasticity of the medium, or whatever the sound is traveling through. So sound travels fastest through solids. Did you ever fall asleep on the dinner table and somebody comes along and sits a cup down at the other end, and you're like, ah, that was really loud, because your ear is right against that hard surface. You can try it right now, Abby. And so it's fastest through solid materials, a little bit slower through liquids, and then slowest through gases. Now that's a general rule. For solid materials, well, all materials, elasticity is also a factor medium to another, like if I grab them, like if you use hearing protectors. Anyone know why hearing protectors actually work? Technically.
Because materials aren't dense, aren't elastic.
Definitely, very much part of it, yes. The design on the density and elasticity.
Prevents them from bouncing.
Very good. So it kind of destroys the energy, that sound wave. It absorbs that sound wave. And the reason it does that is because when it goes from one medium to another, so like the air into a foam hearing protector, it loses speed. So that wave is like, oh, okay, this is a weird new material. So that's why hearing protectors work. Now I get into the cool stuff. Speed of sound. So Mach number is the speed of an aircraft compared to the speed of sound. On a standard day, we're going to talk about this a little bit later today, what standard day is, but if it's 59 degrees Fahrenheit at sea level, the speed of sound is 760 miles per hour. So terms we're introducing now, you'll be using them later. Subsonic means less than the speed of sound. Sonic means right, bless you, right at the speed of sound. Transonic means it's transitioning right at or near the speed of sound to the speed of sound. And then supersonic, the cool one, now are above the speed of sound. So this is a number to be familiar with, 760 miles per hour. Again, in a standard day, that would change depending on temperature and conditions. We will come back to the speed of sound, because I have some very cool videos. But another term is pitch, or frequency, yeah. So frequency can also be called pitch, but it has to do with how close the waves are to each other. So down here, okay, it's just an animal, I'm not sure. Cat's meow is kind of high pitch, I think. But a low frequency is a very low voice. I can't do it very well. Or as you go up, it's a very high. You raise the frequency and the waves are much closer together. Now, which do you think will travel further? A low frequency sound or a high frequency sound? How many say low frequency travels further? How many say high frequency travels further? So, the low frequency will actually travel further. And this comes into play, I'm going to talk about it, oh my, next summer, when I talk, probably your very last class, talk about exhaust systems. And exhaust coming out of a jet engine is a very low frequency. It's also very loud. Page 5-33, figure 549. And there, 90 decibels is a modern turbo engine at takeoff at a distance of 150 feet. And here we have 150 decibels jet takeoff at 25 meters. So this one's in meters, this one is in feet. But at 85 decibels is a sound level where you need to raise your voice so somebody can actually hear you. At that level, you should be using hearing protection. So keep this in mind when you're out in the shop. If people are starting to use power tools, the more time is involved, the more it will damage your hearing. So you might not think about it when you're out there, like, oh, this doesn't seem very loud, but it'll start to damage your hearing. You don't even realize it, and you might become like my dear father, even though I'm telling this story. So he one day, now I can hear much higher frequencies than a lot of people, and so like they'll scrape their fork on their plate or something, they don't have a clue, and I'm like, ow! But also he was sitting in the easy chair in there downstairs. His cell phone fell out of his pocket down into the cushion. He didn't know it, we figured this out later. And then he went upstairs into his study. This was at night. No, he went to bed. We all went to bed upstairs. And sometime during the night, somebody called him, and I was upstairs with my door closed, and I heard his cell phone downstairs buried in the couch of the lazy boy. Of course, he never heard it. So, but then other times there were things that were very clear to my hearing, and he didn't hear them, and I was like, okay, I need to go damage my hearing so it doesn't bother me. I'll do that. But yeah, protect your hearing when you're working with power tools. 90 decibels for 8 hours will damage your ears. Don't think of that as, oh, I only had 1 hour today at 90 decibels, I'm okay. It does not reset. That's cumulative. So as you hear loud noises over time, that'll damage your hearing. So protect your ears. On that note, I have a loud video. Haha. Let's see. Or I'm not sure how loud it'll start out at. But this is a F-18, I believe, at an air show. And how many of you have seen either the Thunderbirds or the Blue Angels? Okay, the rest of you, this is, what do you call it? A spoiler. Sorry. So if you go to a Blue Angels or Thunderbird show, they do what is called a sneak pass. So, oh come on, yes. Or see the pyrotechnics go off. boom, like you feel it in your chest, or if they're flying over, like you feel that. So that is a sound waves coming, and imagine what it's doing to your eardrum when you feel it, like literally on your body shaking. But it's the coolest thing ever. It's totally worth it. Come on. Here we go. So another term is Doppler effect. So you probably notice motorcycle, car, airplane, whatever. It's like as it goes past, and that is changing because it's kind of pushing a sound wave, and then as it gets to you, the sound waves are changing, and that waveform is changing as it passes you. So you are hearing that frequency change, kind of high, and then low, and then boom, it's passed. So here is the sneak attack I was talking about. There we go. So they hope everybody's looking at this, the diamond or whatever they're doing. And then behind it's very low, like, yeah, probably as low as they're legally allowed. Shoo, right over the. So now I've learned, I've seen them, Thunderbirds and Blue Angels a couple of times. So they change it up a little bit, but like, okay, I haven't seen number 2 for a while. Yeah, oh, yeah, there you go.
Which is your favorite, the Thunderbirds or the Blue Angels?
Blue Angels. But I only saw the Blue Angels once, the Thunderbirds I saw, that might change, I don't know.
I like the Thunderbirds better. I like it 16 better.
You like the cheer
There.
coach?
I thought the Blue Angels, when I saw them, this was Joint Base Andrews in Maryland. Blue Angels are first, Thunderbirds are second, and the Blue Angels flew tighter in that air show. But,
The Blue Angels also like crashed, didn't they?
oh, one of them did.
Two like just crashed like a week ago.
Oh, like recent?
Yeah, like pretty sure like just crashed.
Oh, yeah. That's sad.
Yeah.
So now, we have to talk about the sonic boom. So, as the aircraft is going through the air, approaching a speed of sound, that's kind of catching up. This is a very simplistic way, but you don't have to understand it in depth. Kind of catching up to all the sound waves, they're building up, and that's what you see as it looks kind of like this cloud. And so, as the aircraft approaches, you don't hear anything because it's flying faster, it's ahead of its sound, and then you see it and then boom. So there is a really good air show at Battle Creek, usually in July. And last year, I think it wasn't just this past year, they're more careful, but last year there was, I think it was F-35, I forget, Anna remembered, she was there. And they, we're pretty sure they broke the sound barrier, because we didn't hear a thing, and there was a clear cloud on their wing, and they were at us, and it was like, boom, like, ear-shattering stuff. Did awesome. So here's some examples. has what is called a resonant frequency. So all of these atoms in this rod are vibrating at a certain frequency. So on an engine, you have tons of moving parts. So you got the piston moving, and you got the crankshaft, and a whole bunch of other stuff. That's creating certain vibrations within your engine. The propeller, as it is spinning and is meeting air resistance and all that, that has certain vibrations. So when you have two things connected, if they start to have the same vibrations, hey, look at this, here's a rope. How convenient. So if, I'll take a volunteer, here you're a volunteer. So if we are vibrating our ends at different frequencies, I'll let you go up and down a little bit. I'll just kind of cancel each other out. I mean, it's not, whoops, there we have a resonant frequency. So we're just, he's kind of going that way and just kind of going that way. But if we go at the same frequency, we get very large waveforms. Thank you. Which, when it comes to engine and propeller, we're going to talk about that a lot in propeller class. If you match the resonant frequency, what do you think is going to happen to your propeller?
It'll break apart.
Yes. Your propeller blades may depart the aircraft, which doesn't make for happy pilots. So this was seen very vividly. I think this was one of the first, most vivid examples was the bridge. Anybody heard of the galloping Gertie? Yeah. So there's lots of videos out there on it. I'll show a different video in propellers class when we talk about resonant frequency again next year. But this one, I have never seen someone so excited about talking about bridges as this fellow, and it's really funny. So and it shows what happened when the bridge hit resonant frequency.
We're in Tacoma, Washington, and behind us is the Tacoma Narrows Strait Puget Sound.
There are twin suspension bridges that go across the strait. One was built in 1950 and the other in 2002.
Before these two bridges, there was another bridge over the sound, the Tacoma Narrows Bridge, or Galloping Gertie.
It was opened on July 1st, 1940. Because of windy conditions, the bridge started to move. Yep, you heard me right. The wind caused it to move vertically, up and down. That's when the construction workers gave it the name Galloping Gertie.
They tried several things to keep it from moving, but they didn't work, and in November 1940, just a little over 4 months after it was built, it collapsed.
A bridge collapsing like that might seem like a big deal. It was!
Fortunately, though, no one was injured.
The Tacoma Narrows Bridge became an example in engineering textbooks and spurred research into bridge design that is still influencing how bridges are built today.
So the video I showed Frog's class, there actually was a dog that died. There's this one car that was left on the bridge. Everybody else, all the people got off, but the dog did.
The dog just wasn't a very good driver.
All right, take a break and then come back at 1:30, and I'll open up a lab. standard day defines that. Yes, 760 miles per hour, correct. Now, if you ever need to refer to that, that is page 5-32 under Mach number. If you want to highlight 760 miles per hour right there.
How come it's not knots?
It's a good question. I don't know. Why they don't put in knots? Because aircraft are using knots. It's a very good question. Probably so it makes it a little difficult to convert it. So, knowing that for question 8, question 9 says an aircraft is flying at sea level on a clear day. This is just for the calculation. Maybe it's what do you call it? Death Valley. If the aircraft is traveling at Mach 0.7, what is the aircraft speed in miles per hour? So how do you think you would figure that out?
760 times.
Exactly. 0.7 times a conversion factor of 760 miles per hour. 760 miles per hour in 1 Mach. And that would give you your answer. I think that is the trickiest one. The rest are just look up in your textbook and select the correct answer. I will give you until, let's do a strange time, 1:50. So at 1:50, make sure you're back in the classroom, and we'll finish up today's lecture.
Differences in uniform reading. Does that mean temperature and pressure? Like temperature and pressure change, then medium change, right? The one, sorry, it would not be. You know, highlight, I think that's talking about. That answers my question. Does
Alright, I think everybody's back. Looks like it. So, we will continue with lecture, and then you'll have time to finish this lab, plus do the next lab that I'll be assigning you. So now, we're talking about the atmosphere. Wait, it won't be in your book. Page 5-33 to 37. And by the end of this section of lecture, you should understand atmospheric pressure and density. Now, you may ask the question, why do we as mechanics need to know stuff about the atmosphere, about air density? Isn't that just a pilot thing? What are your thoughts? Why do you think mechanics should know? Yeah.
We're kind of the ones that fix the pressurized gas.
Very conditions, we have to understand how atmosphere affects those so we know how to fix them. Also troubleshooting, if your pilot comes back and is like, my engine's not working, you can ask him what kind of conditions is it flying in. So, we live at the bottom of the sea of air. Not much. And because we live at the bottom of a sea of air, we are under pressure all the time. So as you go up, pressure of the atmosphere decreases. So an increase in altitude means a decrease in air pressure. Anyone ever read Dr. Seuss' Yertle the Turtle? Oh my goodness. I don't have the book. I think my parents have it. When I go home at Thanksgiving, I should bring it back because it's such a good book. But anyway, the story is something like this. Those of you that read it can correct me. That Yertle the Turtle thinks he's the best turtle and he wants to be king of the turtles. And so he makes all of his buddies climb on each other's backs. And maybe he wants to see around the world. I forget which it is. Maybe it's both of them. Anyway, all these guys have to stand on each other's backs. So Yertle can be king of the turtles on the very top. So how much pressure do you think that poor little dude on the very bottom is under? He is under a ton of pressure. But as you go up, the turtles are feeling a little less pressure, a little less pressure. So you can think of us as a poor little dude on the very bottom with all these turtles stacked up. That's like all the little air molecules stacked up. So as you go up, there's less pressure until you're king of the turtles, except it didn't turn out so well for poor Yertle. He got a little tipsy. But if you take a 1-inch square column of air and you start at sea level and you go up in the atmosphere, that will weigh, or it will be 14.7 pounds per square inch. So I mentioned this, I believe, yesterday. 14.7 pounds per square inch is how much air pressure is pushing down on you. And I had talked about a barometer that they filled a tube with mercury, dunked it in a bowl, and 14.7 psi pushing down on this mercury made it go up to 29.92 inches, which equals 760 millimeters. So that's why 29.92 inches of mercury height equals 14.7 psi. Now, those of you that are pilots, how many of you would like to take an open, sloshing bowl of mercury along with you? Me neither. So, thankfully, they came up with some fancy instruments called an altimeter that we can look at, and they tell us our altitude or elevation or height above sea level as we fly. You're going to learn all about these in instrument class, but they have these little aneroid wafers that sense air pressure and do some fancy things you're going to learn about to transmit that into a nice reading. Or it can be a fancy Garmin G1000 or some other digitalized version. So with atmospheric density and pressure, we were talking about gases yesterday, which air is a gas. So as you increase pressure, so here we have 29.92 inches of mercury. Here we increased it to going from here, where we have a lot of pressure, squishing those molecules together, and then we relieve that pressure. Pressure goes down. What's going to happen to density, or how tightly packed those molecules are, do you think? Exactly. So as pressure goes down and decreases, density will also decrease and go down. So you could say pressure and density are directly related. What one does, the other will do. Pressure decreases, density decreases. If pressure goes up, then density will go up. Now, how does temperature affect density? So here's how I think of it. When I think of pressure, I think of the turtles stacked on each other. The more turtles we have, the more density we have. But with temperature, I think of cows. So when I first moved to Michigan, I lived with a family that had cows. And I watched the cows in the summer sometimes, and I watched the cows in the winter sometimes. So in the summer, it was very, very hot. The cows would spread out all over the pasture, or they would go to the shady spots. But they would spread out. They were hot. They wanted space. And the molecules of cows would become very much less dense. They're getting away from each other. But in the winter, when the poor cows were cold, the little molecule cows all bunched together. And they got very tight, very dense with each other. Many cows per square foot, whatever the pasture was measured. So as temperature goes down and gets colder, what happens to density? Excellent. Density increases and it gets more dense. So if cows help you out, you can think of my cows. Now, temperature in the atmosphere does kind of a tricky thing. Here we see this is negative and this is positive. So as you go up in the troposphere, which that is where we fly, that's where weather happens. You see a nice big scary thunderhead illustrated in a troposphere. So temperature as you go up in altitude decreases, gets colder, colder, colder. And then it kind of, here in the stratosphere, kind of increases a little bit again, got some ozone stuff, and then decreases. But for our purposes, we'll say, as you go up in altitude, overall temperature will decrease. So, as you go up, temperature, especially if we stay in here, temperature is decreasing. So what does that mean density is doing? So density is increasing if temperature is decreasing. But what is happening with the turtles? We're getting less dense because pressure is decreasing as you go up. So, who wins? Is it the turtles or the cows? Yes. So, pressure drops much more rapidly with the increase of altitude than temperature does. So, the net result is that density does decrease with altitude. So, turtles win the day, cows, sorry, bye-bye. But here's a nice illustration. This is representing our molecules of air. Lots of happy molecules down here close to the Earth. We have high density, molecules close together. And then as we go up, because our pressure is decreasing so much, much fewer molecules as you go up in altitude. Any questions on that? station applications, we've got standards. So they have come up with, I say they, I don't know who they is, scientists. Anyway. So if you are at sea level, what is defined as a standard day is pressure at 29.92 inches of mercury. Hg is a symbol for mercury. And standard temperature is either 15 degrees Celsius, or if you use Fahrenheit, 59 degrees Fahrenheit. And gravity is 32.147 feet per second per second. Per second. Excellent. Now, we've got up, and these conditions all are taken at 40 degrees latitude, which right there is Michigan, so just south of us is a 40-degree parallel. So if you are here at sea level with pressure 29.9 or 2, 15 degrees Celsius, gravity 32.147 feet per second, then you're experiencing standard conditions. How often do you think that actually happens? Yeah, 0.0000%. So we've got stuff like hurricanes coming through. Anyone know a hurricane does to pressure? Do you have a question?
Yeah, so does that change with axial tilt go through the seasons?
It's a really good question. I do not. There's so many other greater varying conditions. I don't know. That might. Because full gravity kind of changes. Yeah, it's a very good question. So, hurricane question. Anyone know what hurricanes do to pressure?
Low pressure.
Very low pressure. Yes. Make it very low. They're sucking things in. Being nasty old things. So now, we are going to talk about types of altitude because yes, we like to make it confusing. If you've been through private pilot ground school, hopefully this will be familiar to you. So, 4 types: indicated, pressure, density, and true. So first of all, we have a nice altimeter here that tells us our altitude. And if you are asked what indicated altitude is, all it means is what your instrument indicates. So whatever you read off of your altimeter is indicated altitude. Now, pressure altitude is a unique thing. If someone could read the definition, somebody who has a Dale Crane dictionary, because, or I could ask a resident flight instructor. I'll have you read it, and then if you have any further clarification. And I believe you'll be referring to Dale Crane's dictionary for the lab, for some of these definitions. Or someone beats me to it.
Pressure.
Pressure altitude.
The altitude in standard atmosphere in which the pressure is the same as the existing pressure, because the pneumatic altimeter operates solely on pressure. Pressure altitude is the uncorrected altitude indicated by an altimeter when its barometric scale is adjusted to standard sea level pressure of 299.2 inches of mercury, or 1,013.2 millibars.
So, Brian, did you have any better, clearer explanation of it? It's a tricky thing, I think. That's sort of it's mainly kind of a standard, but you need it to do other calculations, is the main thing. So, let me go through these and then I'll show the altimeter. so now we're using that number that we're getting, and I'll show you how to do that. Corrected for non-standard temperature. Why would temperature be a factor when we're thinking about altitudes in flight? And it affects density. So density altitude I think of as what the airplane feels like it's flying at. So if I am flying at 3,000 feet on a 100-degree day, how is that going to be different than flying at a 3,000 feet on a day when it's negative 10 degrees?
Airplane's going to act and feel like it's higher than it actually is.
Exactly. So if it's 100 degrees out, what does temperature do to density? It's inverse. So at very hot temperature, I have very low density, so the airplane is trying to breathe air, and there's so few molecules, and the volumes of air it's taking in, it's having a hard time running the engine. Lift is not as lifting, still lifting, but your airplane's going to struggle on a hot day as opposed to a cold day when there's dense molecules are close together, there's plenty of air to take into the engine and to fly through. We're going to talk more about that in a minute. And then true altitude is the actual vertical distance, so mean sea level. That doesn't mean it's a nasty sea, that's just a set line. Mean sea level is what they call sea level. Above that is true altitude. What is your, if you went out there with measuring tape, what are you actually flying at? What elevation or vertical distance, actual vertical distance above sea level? So I want to show you how to read an altimeter. You're going to be doing this for your lab. So I should have had this, I might not have the PowerPoint open for your lab, but some of them will have this little skinny pointer with kind of a triangle at the end. That's your 10,000 foot pointer. So when you're checking aircraft here at Ionia, that's not going to have budged. No. And then it's just like the clock. This guy here, the shorter, chubby guy, is 1,000 foot pointer. And the skinny one is your 100 foot pointer. So what would this altimeter, let's say pilots who cannot answer. What would this altimeter be reading? So I'll say this one is dead on to here and that's dead on there. So 4,000. Pilots agree? Okay, so let me swap over. Whee! Yes, very close up. Let's see if I can not have that glare. So this altimeter, I have it in my hands. Got it out of the closet, therefore it is broken. Let me snapshots of today's weather. This was from last year. But here we've got high pressure systems, low pressure systems, all kinds of stuff going on, all kinds of very non-standard temperatures. So density altitude is hardly ever what the standard is. So mainly, keeping in mind that if it's cool, is it going to be more or less dense than standard? More dense. And if it's hot, is it going to be more or less dense? Less dense. Now here is the tricky thing as far as terminology. This is a nice visual. So here we have nicely cold, densely packed molecules. Here it's hot, they're all spaced out. So there are two terms, high density altitude and low density altitude. So if you hear the term high density altitude, the term high goes with altitude, not density. So if you are at a high density altitude, that means there is very few molecules because the airplane thinks it's much higher than it normally would be. If you're at a low density altitude, that means molecules are nicely packed together and the airplane thinks it's nice and low. And here we go. It's a cold, dry day at sea level. Airplane thinks, I'm nice and low. We've got high density, but it's a low density altitude. If it's hot and humid, airplane thinks, man, I am high. I'm not getting good lift. My engine is not running good. Off the runway I go. I can't fly. He thinks he's at a very high altitude and he can't get the molecules he needs. So, questions on that difference between low density altitude and high density altitude?
It's basically whatever the airplane thinks it's like.
It is.
It has basically everything to do with temperature.
Yep. Pressure affects it, but temperature greatly affects it.
Just temperature affects pressure.
Yes. Yes. So, here, I'm going to confuse you now. If it's a low density altitude, is it actually a high or low density?
High density.
Excellent. High density. If it is a high density altitude, is that a high or a low actual density? I think. Yes. Yep. Yep. Excellent. Yes. So whenever you get the word altitude with it, the high is referring to altitude. Yes.
So can you explain just how the dry air and humid air affect it?
We are going to. Yes. That's next. So one more thing before leaving density is the density altitude part. So here is an example of where you need pressure altitude, there we go, pressure altitude to do the calculation for density altitude. So if you have a little altimeter, how will you find pressure altitude? Yeah.
Put it in standard.
Yep. You just put the 29902 into that little Colesman window, read the altitude off your altimeter. So if we have pressure altitude of 4,000, so here's our pressure altitude 4,000 line. Then we have to know temperature. So if temperature is, let's say, 60 degrees Fahrenheit, so here you have to be careful. The bottom is Fahrenheit, top is Celsius, so make sure you're using the correct scale. So 60 degrees Fahrenheit and 4,000 700-ish, right in there. But if we go up to 100 degrees, but we still have a pressure altitude of 4,000, our density altitude is way up here, almost at 7,000 feet. So that's how much of a difference temperature can make. Okay, before I talk about water, take a break and come back at 35. vapor in it and not as many air molecules, it is much less dense than dry air. So that's why when you're flying on a hot day and it's also humid, your aircraft is struggling to perform well. Besides just being less dense and less air molecules per volume, why else would water vapor and air make your aircraft not want to perform well? Yes.
More drag?
That could be a factor. Thinking more about the engine, yes.
Wouldn't water make it more dense? Because water is denser than air.
So water vapor, having a vaporized,
It's occupying.
is taking up the space that the air molecule would take up.
Oxygen fuel, like the mixture.
Yes. So your engine is taking in this quantity of air, and how many of you have ever succeeded at burning water? Oh no. So water does not make a good combustible mixture. So as your engine is taking this air and trying to burn it, and then part of it's water, it's like it's not making a good combustion. And it sounds like me right now trying to talk. So two terms. Absolute humidity is the actual amount of water in the air. So if I grab a chunk of air and I measure how much water is in it, that is absolute humidity. Relative humidity, here we go again, is another ratio. Is the ratio of the actual amount of water in the air compared to the maximum amount that it could hold. So here at 30 degrees Celsius, where it's nice and warm, because hot air holds more water vapor because it's already giving space for that water vapor to come in because it's less dense, it holds this amount of water vapor. So we would say, well, it's about 28% relative humidity because it could hold a whole lot more water vapor. As we cool that chunk of air down to 20 degrees Celsius, now the air is becoming more or less dense. More dense, because it's getting colder, the clouds are coming together. And so now there's less space for the water vapor, so now our relative humidity climbs because there's less total available space for the water vapor until we cool it down. Here's 10 degrees Celsius, and now we have all of the humidity possibly that quantity of air can hold, so we have 100% relative humidity. So when you hear, oh, we've got 51% humidity today, it's talking about relative humidity percentage compared to how much that quantity of air can hold.
So if you cool that down by another 10 degrees Celsius, but you still have the same amount of
Rain. Precipitation. Rain or snow. So next is dew point. You read my you can see right through the back of it. Whoa. Whoa. So dew point is a temperature to which that humid air must be cooled at a constant pressure, compression, and other stuff, to become saturated. So saturated means it is holding all of the water it possibly can hold. So when it cools down, then comes dew point, and now you've got visible moisture. So, this is a little sad. This is actually the bathroom mirror back at the house where I first lived. It burnt yesterday. But anyway, they're doing okay. And the bottom of the house was actually not too much affected. That was really good. But why? So I had hot water running and the room steamed up. I had changed this light bulb. So what do you think is going on there? Why do I have moisture here and not there?
Once
a bit longer than expected to pre-flight. Bummer. The temperature is now 80 degrees. Your friend tries to reach an automatic weather observation station on the radio, but it's broken. How could you determine current atmospheric pressure and altimeter setting? So, what would you set your altimeter to know what your pressure is? So you want to find pressure, and you do know, I think I heard, what'd you say? Yes, set it to your field elevation. And then you will be able to read your pressure in the local.
You use that to find either or?
Yeah. Question 26, that's the graph. It gives you temperature and you'll use pressure altitude, just find your temperature on the bottom, go up to pressure altitude and over to find your density altitude. And 27 says, after computing the density altitude, your friend starts the engine and conducts his pre-flight checks. During this time, he tunes the radio to the local ATIS to find the local atmospheric pressure at the airport. The ATIS reports the pressure is 25.45. Your friend then dials this number in on the closed window of the altimeter. What will the altimeter read? So now he has the correct pressure in there. So you'll decide what the altimeter would be reading. And what should it be reading if he put the correct pressure in there? Yeah. There should be your field elevation.
How would you know that? For pressure, or temperature?
The pressure, the 25.45 is what the actual pressure is at that from the weather station.
Oh, right, and then you just, they invert like a
Yeah,
distance.
so he put, 25.45 in the Colson window, so now it will read correct elevation.
How would, sorry,
Yeah.
how do we know what the correct elevation, if we don't have one to read in front of us?
So, how would you know which one?
Yeah. Like you said, 5,200, right?
Oh, yeah.
But how would I know that?
Oh, so you would look it up like in your airport manual or something to know what that elevation would be.
On the picture, we're at Denver, and it lists Denver, right?
Yes, for this one it
Okay.
does show it in the full picture. Yeah. And question 28, this is a fun one. It says, for this portion of the lab, the instructor will assign students to an aircraft with a functioning altimeter. So our best one that I went out and checked this morning, Cessna 210. I would like everybody to use, now, it won't take long to do it, so I'm gonna have everybody use the 210, so there's, yeah, hopefully close to the same answers. Don't trample each other, take your time, you can do this tomorrow. Also, we will have time tomorrow. And it says, use the altimeter, determine the pressure altitude, and record below. Call Ione County Airport, and it gives you the number right there, so you can call that phone number and listen what the temperature is. Because you'll use that temperature to come down here on the chart, whoops, boom, find your temperature, and pay attention. Is it Celsius or Fahrenheit? And then come up here, find your pressure altitude, which, how assignment, again, just if you have time. I put up the rest of the chapter. There's some stuff we're not really gonna get to, like more in-depth helicopter stuff. We're just gonna do kind of a basics of aerodynamics, theory of flight, so it really gets into detail with speed of sound stuff and helicopter stuff, and then like weight shift control, so all that stuff we're not going into deep detail, so if you have time and it interests you, feel free to read it, but you'll have a whole class just in helicopters, so I'm not going to steal that.